Right, we'll just wait one more minute and then give people a chance to sign in, and then we'll get started. I'm Jim Madsen. While we're waiting, I'm the Executive Director of the Wisconsin IceCube Particle Astrophysics Center and also one of the Associate Directors of the IceCube collaboration, where I'm responsible for education and outreach. So we also have Marla from Bunker Hill, Illinois, is it? Yeah. Linda from North Carolina, welcome. All right, we'll give one more minute and then we'll get started. And what I'm going to do now is just share my screen. How is your bandwidth tonight, John?
I think our bandwidth is probably okay.
Okay. And so maybe what we can do is, before we jump to the screen share, you guys could just show your video and then introduce yourselves.
Sure, sounds good to me.
Okay, go ahead.
I cannot start my video because the host has stopped it.
Huh, interesting. All right, let me see what I can do on that. All right, well, I'll have to work on that. I'm not seeing where I can start your video. Okay, well, we're going to jump. I'm going to go to screen share and show the presentation. We'll see pictures of you guys anyhow, okay?
Sounds good to me. By the way, how's my audio?
It's very good.
Excellent.
All right.
Okay, so this is our short presentation, a little bit about life at the South Pole and a little bit about IceCube, although usually we save most of the science for the questions. Yeah, just to introduce ourselves, at least by voice. Hi, I'm John Hardin. I'm one of the IceCube Wind Rovers, and I'm here with Yuya Makino, the other IceCube Wind Rover. I'm originally from St. Louis, Missouri, and Yuya's from Japan. Yes, from Japan. So yeah, let's get started. So how do you get here? So to get around, to get to the continent and to get around on continent, you mostly need some special planes with skis. So there's a coastal base for the US called McMurdo, and then the South Pole is very inland from the coast. And to get from McMurdo to the South Pole proper, you take either this plane in the upper left, known as a Basler, or a DC-3, or this plane in the upper right, known as an LC-130 or Hercules. The LC-130 carries a lot more people, but the Basler can fly in a little bit colder conditions. So they typically open and close the station with the Basler, and then most of the heavy lift is done with the Hercules. That's why it's called the Hercules. Down in the left is our little international terminal, which is a box that keeps the wind off of you as you wait for the plane. And in the bottom right is Yuya and me right after we got to the South Pole. We went to the geographic South Pole and took a picture. So next slide, please. So talking a little bit
Oops.
about the station.
All right. There we go. Sorry.
You got it?
Yep. Sorry.
Okay. So a little bit about the station. So everyone knows that the South Pole is cold, but what you might not know is that the South Pole is very high. So we are actually at 9,300 feet of elevation, and physiologically, in terms of pressure, it actually feels higher than that because of how the winds work here. So we're typically between 10 and 11,000 feet of elevation in terms of how much oxygen is there. That's why they tell you not to get in the gym for a week or so before you really start pushing too hard. I got on the treadmill after a week, and it was definitely a humbling experience. The station itself, we call it the elevated station here at the pole, is about 65,000 square feet. It holds 42 people in the winter, and this winter. It uses 450,000 gallons of fuel throughout the year. Most of that fuel is brought by tractors. They drag it in bags. I think about 100,000 gallons to 120 per trip, and they do 3 of these trips. The rest of the fuel is brought on planes. Lower left here, you can see the galley. That's the galley with the windows open when the sun's out. In the winter, the tables, a lot of them get removed, and we actually cover the windows because there are Aurora experiments. Lower right is our winter room. Our winter room is, if you can believe it, bigger than our summer room. You can see there are 4 tiles across on the top. Our summer rooms only have 3 tiles across on the top. And the effect is pretty much that you don't get a bed, or you don't get a desk. All right, next slide, please. We have all kinds of fun here. Wiffle ball is a popular activity in the gym. We always watch The Thing, all 3 versions, right after station close. It's important. And then lower left, you can see Yuya taking a picture of me hanging up our light blockers. That's in the ICL. All the buildings have to block out the light in the winter so that the Aurora cameras don't get overexposed. They only want to look at the green light. By the way, if you see most of the pictures here, you see that are good are going to have been taken by Yuya, mostly because he's a very good photographer. The lower right here, is our station close dinner. The galley did a lot of work. They made, I think it was Zeke being our chief chef, called it a 4.5 course meal. And it was a ton of food, but it was delicious. Next slide, please. Just more about the station. Upper left, you see one of the sides of the station. That's the side that faces into the wind. Excuse me. The station's actually built like a wing to help the wind go over and around it. Top right, you see the planting of the pole marker. Every year at New Year's, the pole actually moves because the ice is shifting about 30 feet per year. So the geographic South Pole sign has to be moved to the new correct place. And the winter rovers for the previous year designed the marker that gets revealed on New Year's Day. So it's pretty fun. You see here in the lower left, all of the different markers that have been over the years. They keep them inside the station on display. Lower right is our power plant. We have 3 generators. We only need to run 1 of them at a time, but we keep 2 as backup, and so we can do maintenance on 1 and run on the other, that sort of thing. We actually have a 4th other backup generator outside of the power plant, just in case. We really don't want to lose power here. That would be very bad. Next slide, please. Oh yeah, the holidays. In the summer, the holidays are great. Everybody kind of goes, celebrates. We got to bake cookies with the galley. There's a gingerbread house competition. On the left here, you see the actual food spread, or the actual dessert spread for Christmas dinner. Upper right is the various gingerbread houses, all pretty good. And the lower right is Christmas dinner. So during the summer, there are quite a few more people here than during the winter. There are probably more than 42 people in this picture. The summer, you can actually get up to 150 people. But the holidays are really nice. They're really fun and really good food. Next slide, please. Oh, the weather. Weather is very important. If it tells us when planes can land, all kinds of stuff. Lower left here, you see our summer meteorologist, David. Upper right, you see Yuya marshaling a plane. It's a thing you can do when the planes start arriving in the summer. Then you have other pictures of the ICL and the sunset. And you also see David launching a weather balloon. They launch weather balloons, I think, almost daily to try and get an idea of the weather patterns and what's going on. So yeah, next slide, please. Oh yeah, more fun. So one of the fun things we get to do is learn outdoor survival in the summer. We learned how to use a bag, which will actually keep 2 people alive for 3 days out, just in Antarctica. It has food and fuel and a stove and everything you need. I'm not sure how well it works in the dead of winter at the South Pole, but it does work in the summer. Then we also have, next to the right is the walk to Mordor. We had 3 people who wanted to get on treadmills and watch all 3 Lord of the Rings extended editions and walk the entire time. Yuya, because he's a smart person, participated in the walk to Mordor in a different way. You can see him on the left in that picture. Then also the Wisconsin, which is the university that we are run through, was in the Rose Bowl this year. And so we got out a sign, and just like the last few times they were in the Rose Bowl, we had Go Badgers, Freeze, and then it used to be Stanford and used to be a few other people. But this year it was Oregon. So it was great. It was a good time. Lower left, you see a penguin in a Carhartt jacket. The big reds are the iconic version of what people wear in Antarctica. But a lot of the people here, if they're working inside but unheated, or they're just outside briefly, or it's not that cold, they'll wear a Carhartt jacket because it's actually pretty warm and it's not anywhere near as bulky. It's very nice. Lower right here is near sometime in late December, early January, Yuya and I went out to the edge of IceCube and played a game of chess. There was a little bit of a time limit on how fast your fingers got cold, but otherwise it was a good time. Next slide, please. Oh, yeah, this is the end of summer. You can see the sunset in the upper left. Very nice picture from Yuya. And then we also got to go to a beach vacation, or a seaside vacation, I should say, to McMurdo. This is the inside of an LC-130. You see all the bags stacked in the middle. People sit along the sides. And then in the back, there's additional cargo and additional bags. Then in the lower left was package mail. Everybody wanted packages. There was a little bit of a logistical hurdle to getting package mail in this summer. So in February, when everybody got their packages, we were all very excited. So yeah, next slide, please. So I'll talk a little bit about the dark sector. There are different sectors here. There's the dark, there's the quiet, and there's the clean air, and they all do different science. In the dark sector, you're not supposed to have radio wave transmission. In the quiet, you're supposed to avoid vibrations. And in the clean air, you're not supposed to emit smoke into the air, as you might imagine. The dark sectors, what the physicists typically use. In it, we have the ICL, the IceCube lab. We have SPT, the South Pole Telescope, which is what you can see down here in the picture with John and Matt, 2 of the grad students who are here for the summer. And then we also have BICEP, which does similar physics to SPT. I don't have a picture of it here, but it cross-checks it and has slightly different wavelengths and things like that. But the dark sector is pretty cool. We go out there a good bit. ICL's maybe 2/3 of a mile from station, and we walk out there. Next slide, please. So the ICL, the ICL's main function is to be the central computing hub for IceCube. IceCube is about a square kilometer in footprint, and below the ice, it's maybe a cubic kilometer. But the ICL sits at the middle of it and computes and takes in all the data from all the strings and all of, we call them DOMs, digital optical modules, but they're really more like pixels, 3D pixels that sit in the ice. And it adds them together and says, is there an interesting event? And sometimes it'll call north if something interesting is going on. And Yuya and I's job while we're down here is to keep the ICL running and to keep everything working, because stuff likes to break. Lower right, you can see one of the computers. This is what we call a DOM hub, and it runs one string. So we have actually more than 86 of these sitting in racks in the top floor of the ICL. You can actually see the two towers on the side and the bridges. That's where the cables come up and go into the server room. And then lower left, the ICL also functions as a sort of clearinghouse, and we get cargo in, we support other experiments and prototypes for IceCube upgrades and all sorts of things out of here. So yeah, next slide, please. The science. So let's keep going if we got time. So the way IceCube works is I mentioned these pixels, and you can see an illustration here of where the pixels are. The pixels start about halfway down the ice, and then they go all the way to bedrock. And I think they're what? Oh, they're more than a kilometer high, or just about a kilometer high. And there's about 60 DOMs from the bottom of the set of pixels to the top. It's a really big detector. And the reason it's a very big detector is neutrinos interact with what's called the weak force, and only the weak force. The weak force, as you might imagine, is pretty weak. And so they almost never interact. So you need a lot of stuff to see them at all, or to see them with any sort of rate, which is why IceCube has to be so big. So if we go to the next slide, please. So the way it works is the neutrino comes in and it turns into a charged particle when it interacts through the weak force. And charged particles, they interact all the time. They interact with the electromagnetic force, which is much stronger than the weak force. So the charged particle ends up producing Cherenkov light. Now, Cherenkov light is a little bit funky, but it's not too bad. The way it works is, you may have heard that you can't go faster than the speed of light. That's only true that you can't go faster than the speed of light in a vacuum. You may also have heard that light travels slower in water. So if you stick a pencil in the glass of water, that's why it bends. So you're perfectly allowed to go faster than the speed of light in water. And when a charged particle does that, you get the equivalent of a sonic boom, you get an optic boom. And so you get this cone of light that comes out of it. And that's mostly what we're picking up in IceCube. We're picking up these cones of light. The bottom left here, you see a little bit of an illustration of a DOM. The DOM is, I don't know, maybe a foot, it's about a foot in diameter, maybe a foot and a half. The entire bottom half is this pixel I was talking about. We call them photomultiplier tubes, PMTs, but you can think of them as very sensitive pixels. The upper part of that is computing and electronic support for that pixel. And that's what looks at it. It says, did we see something? And then it decides if it wants to send it to the surface. Next slide, please. So what do we actually see? So these are sort of our visualization of the IceCube readout. The size of the sphere here will tell you how much light a pixel saw, and the color tells you when it saw it. So the red is the earliest time it saw it, and the blue is the latest, and it just goes in spectrum. So the amount of light we see tells us the energy. We can get sort of a direction, and we can also get a pattern. These are some of my favorite things to look at. Even though humans aren't picking out neutrinos by eye, it's really cool to see it happen just, you can do that for some of these. So this top picture, you see that something came in, it interacted, and then there was kind of a boom of light, just an explosion of light right in the middle. So the only particle that exists that can come into our detector without us seeing it is a neutrino. Everything else we will see as it goes through our detector. So we know this had to be a neutrino. We didn't see it until it interacted right in the middle. We also know that it's probably an electron neutrino because they tend to make these sort of explosions of light and not travel very far in the ice. You look here in the bottom left, that's more typical of a muon neutrino. It kind of comes in at the edge and it just goes straight through, turned into a muon. Muons tend to go they keep going. They don't get stopped by the ice. They aren't bothered anywhere near as much as electrons are. We know it's a neutrino, however, because you can see it's coming down from the bottom. And there's no particle we know of that makes it through Earth and comes and can get it to the ice unless it's a neutrino. It's the only particle that can do it. So that's sort of what we're doing. Now the computers are doing this with, specialized patterns and all kinds of other statistical fitting, but that's the general idea of what they're doing. And it works pretty well. Okay. So next slide, please.
John, I think let's go to the Q&A.
Okay, let's go to Q&A. That sounds good. That's a good summary of the IceCube science.
Yeah, and then people can ask about
or at least how we work.
Those events, okay? So, all right.
Okay.
So, thanks very much. And let's see, I can't. Okay. All right, so let's see if we get some questions here. All right.
Got 3 already.
Yeah, I'm going to see if I can first just give you no. Yeah, I'm just not getting. I'm going to try making you the host, John, and then see if we can. All right, and then let's see if now you should be the host, and then let's see if you can turn on your video.
Hey, looky there.
Look
there
at
I am.
that. Fantastic. They would rather look at you. All right. And slide over there, Yuya. There you are. Hi. All right, let's go to some questions. All right, so and the first question is an interesting one. It says, why are there only 8 deep core strings? Why aren't they all deep core? And what do they detect that the others don't?
That's a very good question. Eagle eye. The deep core is a set of IceCube strings that are closer together than the typical IceCube strings. And the reason we do that is IceCube is always working with a trade-off. We want to see a lot of neutrinos, which means we want to be very big. And we also want to be able to see neutrinos that are of a sufficiently low energy. So we want to be close together, because the lower energy you are, the less the light spreads out. So there's a little bit of a trade-off done here. So most of IceCube is not deep core, but the last 8 strings, they put near the middle of the detector, and they made them close together to get what we call a lower energy threshold. They are the technology is identical. It's exactly the same DOMs and everything that go down there, and they come into the detector in the same way, but they're just closer together. That's really what it means. And in fact, the IceCube, the near upgrade is going to expand deep core, so we get a little bit more information about these slightly lower energy neutrinos.
Yeah, great. All right, I'm going to jump over to the other side here on the chat, and the question was, do some neutrinos travel all the way through the Earth?
What?
Do some neutrinos travel all the way through the Earth?
Oh yeah, neutrinos travel all the way through the Earth all the time. It's no problem at all for them. The they basically don't see the Earth. We only see the little small fraction of them that see anything about the Earth. The thing I like to talk about is the neutrinos from the sun. There's about 400 trillion of them that goes through every person every second, and it doesn't bother us at all. The weak force is very, very, very weak.
Yeah, very good. The next question says, do you see a difference between the counts of neutrinos between day and night in the South Pole? And maybe you could say a little bit about what day and night means at the South Pole.
Yeah, that's a good question. So I'll start with day and night here. So the South Pole is almost unique, other than the North Pole, in that we only experience one day and one night per year. So typically our sunset and sunrise are at the two equinoxes. And that's the only time that we see the sun set and rise. Otherwise, it's doing a slow spiral up and a slow spiral back down. Which, you know, it's kind of cool. As for day and night, we don't see much of a difference. The Earth isn't doing any neutrino blocking, so we see pretty much the same amount of neutrinos from any direction. And most of what we can see are either coming from cosmic rays from the atmosphere or astrophysical neutrinos in particular. Either or, but those do not have a preferred direction on the sky, as far as we can tell yet, although there's definite interest into looking at that.
Yeah. I'm going to interject with a question for Yuya. So what has the challenge been like trying to take pictures as it gets colder?
I don't know. Once you go outside, your camera is going to be frozen in, I don't know, 1 minute to 3 minutes. So it's always challenging to keep it warm.
Yeah.
That's what I can say.
About 1 to 3 minutes is most you get, right? Okay. Yeah.
And it's cold.
Yeah. All right. The next question says, what does a typical day at the pole look like for you, and how much time per day are you spending outside?
Let's see. For me, I wake up. Typically in the morning, we're doing something, either something like this. There's a quantum class we've been doing. Sometimes I'll call home. Then we have lunch. After lunch, these days, the satellite goes down. If the satellite's down, we don't have as much internet. So I like to go work out. I code a little bit, do other things. Then for dinner, we also fix IceCube in between here if it's broken, or we do special runs for it as well, depending on what the emails say in the morning. Then we go to dinner. And after dinner, we hang out with people from the station one way or another. Typically, we spend at most an hour outside per day, maybe half an hour to an hour. It's pretty cold. You can last for a while out there, as long as you're moving, but it's not super pleasant, and your goggles fog up. If there are good auroras out, personally, I'll be in and out of the station quite a bit. Taking pictures, warming up my hands in my camera, taking more pictures, warming up my hands in my camera, things like that. It's fun. We find things to keep ourselves busy down here.
Okay. Another good physics question. How do you differentiate between a neutrino coming from the sun and those coming from deep space?
That's a very good question.
Yeah.
Thankfully for us, we actually cannot see most of the neutrinos that are coming from the sun. The neutrinos from the sun have an energy of less than 10 MeV. And the lowest energy neutrino we can see is what? 10? We can see it down to a TeV? I thought we could see 10. Few TeV. Yeah, that's what I thought. G? Yeah, few. Few GeV? Oops.
On
Okay.
the-
We can see a few GeV neutrino, which is about 1,000 times as much energy as the lowest energy, or as the highest energy coming from the sun. So the bigger trouble we have is differentiating neutrinos that are produced by cosmic rays in the atmosphere and neutrinos that are produced by deep space, astrophysical neutrinos. We end up having to use what's called a veto. We look to see if there's a cosmic ray shower at the same time we see the neutrino. And if there is, we say, no, it probably came from the cosmic ray shower, not from astrophysical sources. We see maybe one astrophysical neutrino per month, actually. We get alerts when that happens, and we're pretty happy about it.
And then you might need to provide a little context. This is from Christopher. He says, what's the status on your popcorn experiment? So maybe you could remind people that weren't on the last few weeks what's been going on.
So the popcorn we got from McMurdo, as it turns out, was very, very dried out. So we looked it up, and one way to solve this issue is to add water back. The key, however, is to figure out how much water to add back. So a couple weeks ago, we made about 18 different preparations of popcorn, half batches, and added different amounts of water to them. And we made a curve of how fluffy the popcorn was at the end of this. And we got a nice peak, right at about adding 10% of the popcorn's weight with water to it. And that was the fluffiest popcorn. I did some follow-up, and it turns out the popcorn had between 3 and 4% water in it to begin with. And so the internet claims that 13.5% water is the optimal fluffiness for popcorn, and we actually agree with that, surprisingly enough. So we've been trying to get a good assembly line now of undried out popcorn that we can have for movies on the weekends and whatnot.
Cool. Yeah, that's a neat, neat little diversion for you, right? Yeah.
Mm-hmm.
Okay. The next question looks at practical applications of neutrinos. Have you considered using neutrinos for data communication between the US and IceCube?
That would be very interesting to do. It'd be pretty hard to do this as any sort of large-scale communication. So it'd be hard for we certainly couldn't send neutrinos to the US from here. And even if we could, you'd have to have a detector the size of IceCube to see whether or not you're sending them, or close to this, on the order of the size of IceCube. You wouldn't save a whole lot over sending light. However, there have been talks of experiments of sending neutrinos produced at a beam in the north and then having IceCube detect them, which I think would be pretty cool. I don't know how far along those projects are, but there is talk about that.
Yeah. One of the challenges, right, is to get a high enough energy ones, neutrinos, that we can see them, right? That's the
Yeah. And you could do it with Fermi, I think.
Yeah. So this is kind of a follow-up to that over on the chat. What are practical applications of the data that you're being collected, and how can it be used in the future?
That's a very good question. We do pretty basic science down here. So there's a little bit of a long chain between when we collect it and how it gets used. But neutrinos are one of the biggest mysteries still in the Standard Model. They're the thing we know the least about. The fact that they have mass at all is a pretty recent discovery. Now, the weak force is short for the weak nuclear force. So understanding more about the weak force and how things work gives us more understanding about nuclear reactions and how things are going on in that they're very small. But understanding astrophysical sources of neutrinos also give us an understanding of how things are going on in the very big. So we're looking at very high energy sources on the sky. So we need to understand how neutron stars merge, how black holes merge, and understanding how neutrinos come out of that will give us more information. Now, in terms of practical technology from neutrinos in the near future, that's not likely. But in terms of understanding how astrophysics works and what's going on in the sky, it's hard to say what technology comes out of it. And it could be quite a bit. There's also technology that gets pushed just by the mere development of neutrinos. When we deployed the DOMs, we had no idea how much pressure you had as ice went down. As you went down into the ice, as the ice froze, you had no idea how much pressure that produced. We also didn't know how clear the Antarctic ice was. As it turns out, the ice down there is much clearer than we thought it was. Again, that's more information about ice. That's more information about other sorts of things, just as we learn more stuff. We're investigating the stuff we don't know very well. And that's, to me, that will come, practical applications will come from that. But it's hard to say exactly what will.
Yeah, just as a quick comment, we actually have a paper from a decade or so ago where by looking at the optical properties of the ice, we could estimate how fast the wind was blowing 30,000 years ago, right? So,
really?
Yeah, so.
Nice.
Yeah. Okay, another one. What job still needs to be done when the detector is running normally? They want to know if you're doing something, I guess, down there.
So that's, yeah, no. There's a few different jobs. One of them is if the detector is running normally, sometimes we have to do specialized runs. We calibrate the DOMs, we calibrate all of the DOMs, I think, twice a year. And we calibrate our VTO system once a month. Excuse me. Oh, sorry about that. We have fire alarm testing going on right now.
All right.
You
look pretty calm, so it must just be a test.
Yeah, they told us it was a test. Yuya and I are actually both on fire team. If it were not a test, we'd be running out of here. I'm sorry.
Yeah.
We also send data. So about, I believe, 100 gigabytes a day we send north over our link, the same link that the ISS uses, actually. But IceCube produces a terabyte a day of data. So we need to actually replace hard drives that this is getting written to on a regular basis. Sometimes the detector will be running just fine, but a piece of the detector or a piece of our computing software will break. And because the detector is robust, it won't interrupt data taking, but it will need to be fixed. We also have to shovel snow off the ICL. May surprise you, but snow shoveling at the South Pole is a thing.
And almost endless, right?
Yes, it keeps going.
Yeah. Yeah. And maybe you could say, do you get a lot of snow, or why is it we have to keep shoveling the snow?
So we are the driest desert in the world. I think we get less than an inch of precipitation per year, but there's plenty of wind, and the wind will blow in ice crystals. It's actually not mostly snow, it's mostly ice crystals, and it will just blow it in from the rest of the continent and start accumulating on things, and it eventually becomes a problem. Yeah. So you have to stay on top of it.
That's good, yeah. Okay, a question about, do you work with other neutrino experiments like the ones associated with Fermilab, or maybe the one in Japan?
I don't think we do much direct collaboration. I don't think we're sharing data in real time with them or anything, unless there's a supernova. But we do combine our results with them. So the different experiments, different sizes, accelerator versus not, these all look at different aspects of the neutrino properties. There's actually quite a few unknowns in neutrinos that have to be measured. And these are all looking at different parts of that. And we expect that all of those parts should fit together nicely. we call it unitarity. It makes a nice triangle if you draw it. And we're hoping that when we pull all of these numbers together, we actually get what we expect back out.
Yeah, and we work, there's a much smaller detector compared to IceCube in the ocean, or in the sea, actually, the Mediterranean.
Oh, yeah.
Antares. And so we have some joint publications with them. And there's another one in Russia at Lake Baikal. So that's, again, much smaller. So there's a few, but we're mostly very collegial and work together with all the experiments.
Yeah.
And so now here's a question. This one almost always comes up on these webcasts about what's the situation with the COVID-19. How are you handling the COVID-19 news there?
So big news on station. We haven't had a plane since February 15th, and we won't until at least mid to late October, unless there's a medevac. So there's no chance of infection here. You may notice you and I aren't wearing masks or social distancing or anything. Hey,
not for health reasons.
That said, yeah. That said, it's a little difficult just hearing news from the north, not being able to be there for friends and family, and it's we can't do anything while we're down here. We just have to listen. So it's okay. We're doing okay down here.
Okay. Yeah, that was the last question I think we had from our attendees. Anything else you would like to tell people about the living and working at the South Pole?
Let's see. It's great. Personally, I'm having a really nice time down here. The hardest part is, of course, just being away from everything, but it's a really cool place to be, and it's really great to be part of the science that's going on.
Cool. And maybe you could give us an idea, how frequently are you seeing auroras now?
Oh.
Like every day?
Yeah, I'm maybe not quite every day, but that's just because the wind blows and it blows enough snow in the air that you can't see them.
Yeah.
But we see them, I don't know, at least 3 or 4 times a week.
Very cool.
Now the good auroras is a different story. Those come. We'll have to see how often those come.
Okay. And then we got one more question that came in, and I think you've talked about this before in some of the earlier broadcasts, but is it tough being away, from people?
So yes and no. For me, it's hard being away from family, and it's especially hard being away from family during times like the holidays. That hit me a little bit harder than I was expecting. I'm very happy to be down here at the pole, but I do miss people, and I miss being able to be with people.
Okay. And I think we'll make this our last question, asking about the greenhouse.
Yeah.
I don't know,
so we do have a greenhouse. We do everything hydroponically here. The Antarctic Treaty actually does not allow us to bring soil down. But we grow, I volunteer there on Wednesdays. You volunteer too sometimes, right? Yes, yeah. And, we plant things, we grow things. Our big producers are tomatoes. We also grow a ton of cucumbers. And then periodically we produce all kinds of different greens. We have like chard and mustard greens and mizuna, kale, lots of kale, ton of cherry tomatoes, all kinds of stuff. It produces quite a bit. I think we get up to, I don't know, 20 pounds of vegetables a week at least, maybe more.
Very cool. And so we have a request for the next webcast to just could you include a picture of the greenhouse next time? So we'll try to,
Okay.
get that taken care of. All right, we
See what I can do.
appreciate you taking the time to talk to us, and you're looking good. So whatever you're doing, keep doing it. Okay. All right. And
Will do.
thank you so much, and we'll talk to you next week.
Okay. Talk to you next week. Thanks, everybody, for coming.